NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, ladies and gentlemen. How's everyone tonight? Good. Well, thanks for coming out to join us, as always. JPL has been engaged in several programs over the last few years that have developed new robots and software that can help out in terrestrial disaster scenarios or hazardous environments. In particular, the RoboSimian and Surrogate sibling robots have been designed to move through human environments after humans have had to evacuate and execute key manipulation tasks that will ameliorate the situation. RoboSimian will be put to the test against an international field of robotic competitors at the DARPA Robotics Challenge this June 5th and 6th at the Pomona Fairplex. Tonight's guest is currently the supervisor of the Robotic Vehicles and Manipulators group at JPL. His areas of expertise include space robotics, bio-inspired robotics, novel mobility systems, robotic manipulators, and under-actuated grippers. He graduated from UC Berkeley in 1996 with a BS in mechanical engineering with an emphasis in controls and robotics. As an undergrad, he was involved in research covering the design of composite material parts, the design of human amplification mechanisms, and the finite element modeling of bones. In 1997, he received his MS in mechanical engineering from Stanford University, concentrating on mechatronics and robotics. At JPL, he's divided his time between research and spaceflight robotics. On the research front, he conceived and led the development of the bio-inspired Lemur series of robots, as well as acting as the lead mechanical engineer on a number of other robotic systems. He has also acted as the lead robotic engineer on several DARPA studies of subjects such as orbital telescopes and humanoid robotic mobility. On the flight side, his major role has been as the cognizant engineer of the robotic arm for the Mars Science Laboratory, where he was responsible for the design, fabrication, and testing. Previously, he had also been responsible for 2 elements of the Mars Exploration Rover chassis. Currently, he is leading the development of the Gecko Gripper tool for the DARPA Phoenix flight program and the RoboSimian robot for DARPA's Robotic Challenge. Ladies and gentlemen, please help me welcome tonight's guest, Mr. Brett Kennedy.
Thanks, Mark. So today we're going to talk about robots that are here to help. And really the title of this is Robots to the Rescue is more about the alliteration than it is literally the idea that robots are going to come and they're going to pull people out of burning buildings. That's a grand goal, but it's not really where we are today. So I'm going to explain a little bit about what these robots are really designed to do and some of the technologies that we use to make that happen. So disaster response means mobile manipulation. Now, if you can get someplace that is under in a disaster scenario and do something key to help the situation, that would be fantastic. And to do that, you both have to go there and you have to do something once you get there. So this is actually different than other areas of robotics where it's mostly about the going, or areas of robotics that's mostly about the doing. So quad rotors are really great at going places. Industrial robots, robotic arms are really great at assembling cars. This is something in between those two things. And the types of technology, sometimes it can borrow from either side of that spectrum, and sometimes we have to do things differently because we need to both go and do. So one particular emphasis tonight is going to be the DARPA Robotics Challenge. And that's a competition I'll explain a little bit more. And it really is the place in research where mobile manipulation as its highest expression for practical use. So there's a lot of really interesting research that's more on the academic side and how you can do these things. But here we have robots that really need to actually make things happen in real time and in real conditions, or at least mostly real conditions. So JPL's effort here, RoboSimian, both refers to a robot, and as I'm going to explain, it also describes a set of technologies that we can use for various purposes. Okay, so let's set up the problem a little bit. What is the robotics challenge? So that's a lot of words. This is what DARPA says the robotics challenge is. But really, it's these words in yellow that are important. It's the mobility and dexterity to maneuver in degraded environments typical of disaster zones. So otherwise known as humans built something and it fell down. And then to be able to deal with tools and jobs that are sort of the nature of what a human could do in that situation. And December of 2013, we took part in the DARPA Robotics Challenge trials. Those trials are laid out here. And this gives you a feel for the general scenario. Now, to set this up in particular, the entire challenge was inspired by the Fukushima disaster. And in Fukushima, there were a couple of things, very simple things, that had they been done would have limited the damage overall. Now, this is something that has affected people worldwide. And had a robot been able to go into some of the reactor spaces and done something as simple as turning a valve, that would have released some hydrogen that had accumulated and would have prevented secondary explosions that caused a lot of the damage. Because there was not a robot that could go someplace and do something as simple as turn a valve, there was all of this additional damage. So, inspired by this, DARPA created the DARPA Robotics Challenge. And as you can see, it starts out with the idea that the robot needs to get to the location. Now, DARPA has chosen a particularly interesting way of doing that, which is to say the robot needs to get into a human vehicle and drive it, and then get out of it. Now, does a robot really need to get into a vehicle to get someplace? That's arguable. We have robots that would actually roll themselves to the location. But as a problem, it's very interesting because it is a very human-structured problem to deal with, the inside of a vehicle. It's really just designed around people and for no other reason. So if you can drive a vehicle, then you can do a bunch of other things as well. After it gets out, it walks across debris, sort of a rough terrain, and then it needs to get inside the building. Now, the assumption, again, is that this is a degraded environment, i.e. things have fallen down. So it needs to reach in and grab things and move them out of the way of a door, then goes through the door, climbs a ladder, cuts through a wall, and carries a hose, and then finally we get to the valve part of it. So at the very end of all of this, there is the one task that's kind of analogous to what we would have done in Fukushima. But along the way, we're trying to exercise all these other capabilities. They're very human in nature, but need to be carried out by a robot. And all of these tasks, other than the very direct things that they're doing, they're also trying to exercise certain abilities of the robot. So perception. How does the robot see the world and take in that information? And what does it do with it? Mounted mobility, that's driving the car. Dexterity, so what can the robot do in a dexterous manner? And we'll talk a little bit about the difference between dexterity and just general manipulation. Decision making. Now, the decision making in this case is not necessarily the robots alone. It's also the way the operators use the robot and their decisions. Dismounted mobility, so obviously when the robot's outside the vehicle. And strength. So you could build a gossamer system that really couldn't ever do anything, even though it could go through the motions. And in this case, we really wanted some systems that could put some oomph, actually physically interact with their environments. So we're going on to the finals, and I will make an unabashed plug here, since you're all, I'm pretty sure, are local or local-ish. In Pomona, on June 5th and 6th at the Fairplex, will be the finals. There are, I think at this current count, something like 28 different teams. As Mark mentioned, they're going to come from all over the world. Japan, South Korea, Germany, at the very least. And there are also a lot of homegrown teams, both from universities and large companies, but also some very interesting teams from people who are just trying to build interesting robots in their garage. So you can come see the wide spectrum of folks that are going to show up to do this. And if you want more information, roboticschallenge.org will get that information to you. It is completely open to the public, and it's really set up as a spectator sport. That really is what DARPA is hoping for here. So tell your friends, bring yourselves, schools. Okay, so what did we build and why? Well, has anybody in the room ever been a kid or had a kid? All right, yes. So you're probably familiar with a certain little curious monkey. As you already gotten from the name, RoboSimian is inspired by our simian cousins, apes and monkeys. And while I didn't use these particular pictures as inspiration as I was reading these stories to my daughter, I'm like, that's exactly what we're talking about here. So really a generalized system. And when I say a generalized system, people are not a generalized system. We have very distinct legs. Our legs are good for walking. They're reasonably okay for running. We've got arms that are really good for grabbing things, hands that are really good at holding onto things and doing dexterous manipulation with your hands. But we're what biologists refer to as a derived species. The apes are much closer to the base of the tree, and they are less derived, more generalized. Among other things, the fact that their limbs can be both used as arms or legs, that they have hands. And this is a fascinating thing. I discovered that, at least in English, and I haven't discovered any other language, we have a real problem with describing what is at the bottom of a leg attached to an ape or a monkey. So they call them feet, but they're not really any different than the hands. So there should be some sort of generalized terms for those as well. Biology apparently has skipped that particular thing. Going a little bit beyond that, axis and planar symmetry for, someone pointed out this is their favorite phrase of the entire presentation, orientation agnostic functionality. So this is a very fancy way of saying that it doesn't really matter which way the robot's pointed. What it can do in any particular direction is the same. It can see the same, it can grab the same, it can move the same. And something that goes along with that a little bit is this hemispherical coverage of perception. So it can see in any direction within the hemisphere. So that's sort of the middle bunch, and that's really the Curious George version of it. The other things at the top, this is actually going to yet a different children's story. Slow is smooth and smooth is fast. So this is the tortoise and the hare. And as a design philosophy, we picked the tortoise on purpose. And it is not a hare, and it doesn't go fast, but it's very sure about what it does. And because it's sure about what it doesn't make a whole lot of mistakes. It doesn't fall down. And that means that overall, it's faster. And then the final little bit of it is optimize it towards early deployment. So this is not an academic exercise. This is something that we hope to put in the field as soon as possible. And as such, we needed to keep that in mind when we were designing the robot. And so this is what we proposed. So when we told DARPA we'd like to build something, this is what they saw. And it's this near-term fieldable system for disaster response that's relatively inexpensive to, and relatively being the important term here. And then some of the stuff that we thought we could do with this kind of robot. This is, you're seeing the ladder climbing, the driving the vehicle, the opening of the doors. Maybe with all of those robots at the same time would be great. That's kind of where we thought we would be. And this is where we ended up. So not that different. It's got some few extra little bits. You saw this graphic on the left earlier. I want to point this out in particular there as a local flavor. This was done by a student of mine, Noah Ecker, who's at Art Institute. And he came and worked with us over the summer and did some fantastic illustrations like this. Now you can see that there's a little bit of a difference between the dramatic representation and what we were actually building. But we aspire to that. So we start out with the M&M Man, which is what people quickly started calling it. From there, and I will explain a little bit more of that, we moved on to a concept that was developed here in conjunction with some of our industrial designers and artists that are in residence at JPL. And then we were able to build that into that first system for December of 2013. And you can see its two main poses. Whoops. The two main poses seated on its wheels. I'll talk about that a little bit. And then the more obvious quadrupedal stance that it takes over rough terrain. So, as I mentioned, we worked with artists and industrial designers here at JPL because one of the really important things, I think, is that we find a way to get people to accept the idea of robots. So despite the best technology, as anyone who has picked up different types of smartphones will know, people like stuff and will pick things up and use things for non-rational reasons. So we needed to look at the design of the robot. Now, we're a Western audience in general, I think, in here. And Western audiences will give you, generally speaking, one of two responses to robots. It's either the Terminator or it's C-3PO. Neither of these are good. One of them is a completely ineffectual system, and the other one is scary. So we needed to pick something in the middle. And in particular, this robot needed to be able to go into disaster areas and get used. The people that go to disaster areas are first responders. First responders use tools. They use professional-grade tools. What does a professional-grade tool look like when it's a robot? And that's what this system was intended to be in concept. So we spent a lot of time looking at different emergency response vehicles. We looked at the uniforms that are worn by first responders. You can see sort of in the middle, there was a lot of time spent looking at the way cars are designed. The front of a car is a face, and the expression on that face tells you a lot about the type of people that will accept that particular car. So very expressive. And so I think we would like very much to continue that, and we did our best. Now, the practical realities of building a prototype robot mean that we really weren't able to achieve that final artistic goal, but we think we did pretty okay. And as evidence, Exhibit A was this little girl. When we went to the trials, she won the photo contest, and her prize was that she could have her photo taken with any robot she wanted. I'm pretty sure the organizers thought that robot would be not us. But they came and said, she'd really like the picture with RoboSimian, can we do that? And sure. And all of you, I'll be interested to talk to you as well about your perceptions of what RoboSimian looks like. But she thought it was cute, and I'll take that. Whoop, here we go. So what does it do, and why does it kind of look like it does? And so moving around, we need to be able to walk. This is in the upper left, you can see it walking around. This is kind of a neat graphic. This is actually captured from a physical simulator that we have here at JPL. It also gets used for things like figuring out how the landing systems will fall out of the sky onto the surface of Mars. In this case, we're using it for a slightly slower application. And so you see it walking around. You can see you can probably just make out the little red dot that's on the ground. That's its center of gravity. You'll notice that keeps that center of gravity within what we call the stability polygon. We'll talk about that a little bit more. But basically, it means this thing's a very stable system. And that's just walking around. If you look in the top middle and the top right, this is the fact that this robot, because it's got hands at the end of every one of its limbs, can grab onto its environment and stabilize itself by anchoring. And so it can be on a ladder, climbing the ladder, if it can move around and hold itself there without any issue. So it's not balancing itself in any way. So it's a very stable way of going about things, very sure. On the lower left, you're seeing what happens when we start to manipulate the world. So there's just a tripedal stance, and you can grab stuff and move things. In the lower middle is what happens if we actually go into a more bipedal stance. Now again, we're not balancing here. This is actually supporting itself on a very big piece of hardware and then manipulating that hardware. So bimanual operation. And then in the lower right is just an example of a valve turn that we're doing from a tripedal stance. Now, It's got some other aspects to it. One of the really key things is that, like apes, it's really about moving around in a 3D environment. This is what it's really good at. It can move across flat ground, but really what it's there for is to move around in a 3D environment. And to the best of my knowledge, it is the only robot that's demonstrated doing pull-ups. I could be wrong, but I believe that is true. And now you're seeing some of the other aspects of it, the design, the dexterity of the limbs, and we'll talk a little bit more about this in detail, but the fact is that this has the same number of joints in effect that you do in your arm. However, it is not constrained when it's doing this. Now, my arm goes from here to here. This isn't very much range of motion. If I could spin my elbow around 360 degrees, that would be more like what RoboSimian can do with these limbs. And you're seeing some of that in this video. And that has a lot of advantages. So that was halfway to the trials. And then here's the trials. So as I mentioned, we can move across flat ground by walking, but it's really inefficient. If anybody's ever gotten on a bicycle or anything else, you know that the most efficient way you can get around, and this is actually, mathematically speaking, you are about 10 times more efficient rolling than you are walking. And it doesn't matter how good at walking you are. It just is true, right? So about 4 weeks before the competition, we said, you know what, we really want to roll. So we gave it wheels. And so it sits down on its wheels and declares victory and rolls away. Now, do we really think that real disaster zones are going to give us nice flat ground to work on? No. But that was the competition. That was what they gave us. So here are some of the other challenges of the competition we talked about. Here's turning valves. So from our nice seated position, we can use our upper limbs quite easily to do the valve turning. And then when we got to get down to it, we can get right on our limbs and go for a walk. The cinder blocks are actually an interesting problem because they are so regular, even though they're supposed to be debris, they're very regular. That in itself actually creates some issues. That, by the way, not supposed to happen. But it's an illustration of how stable this thing is. We can make mistakes without the robot falling over. We were the only robot to compete that did not use a physical safety belay to keep it from rolling over. And then going back to the doors, here we go. As an added little fun thing about the doors, there was enough wind that it blew the door into the, after our opponents had opened the door, a lot of them got the door slammed in their face. We did not. And clearing the debris. And we're back to the walking. Notice that there's one person running the robot. There's one computer. There's one monitor. We'll talk about that a little bit. And we're good. Just another fun shot of a transforming of the mobility modes. Just because it's fun to see it. Okay, so we made it to the competition. The fieldability aspects of this. It fits in a standard, relatively small box. That box goes into a bunch of crates, and so we can basically, and is often the case, it's a military mission to go provide aid in disaster areas. We can load tens of robots, if not more, into a standard cargo vehicle used by the US military and get these robots anywhere in the world in less than 24 hours. In our particular demonstration of this, which was not necessary, but we take great pride in it anyway, we shipped the robots to Florida, which is where the trials were, pulled the robot out of the box, and had it running in 42 minutes. I take great pride in saying that some of our opponents, it probably took them the better part of 24 hours to get their robots up and running. So this told me that we were doing a lot of the right stuff. The other thing is that you'll notice in the bottom picture, this is, again, the setup. There's a robot, there's a person in a folding chair, there are a couple of people just to keep him company, and 2 monitors and a computer. That's it. This is what it takes to run the robot. It was so empty inside. This is done at a NASCAR track. It was so empty inside of our garage that people walked through there and were about halfway through before they realized that they were walking through our garage. They thought it was just an empty space. Other teams filled, and I do mean filled, their garages with computers and monitors and people and stuff. And so again, told me that we were doing what I felt to be the right thing. So talking about those limbs, so 7 joints. So I'll teach you a little robotics. And if anybody came to the talk a couple of years ago, you might remember this version of it. But you've got 7 joints. You just don't seem to, you normally count it and you say 1, 2, 3. But for a roboticist, you actually have 3 because you can get 3 rotations out of your shoulder. You have another 1 at your elbow and another 3 at your wrist. So those 3 effective joints that you have are translated into this design as discrete joints and discrete motor actuator chunks. So again, it can do basically everything that you can, but has all of this extra rotation that allows to do things like fold the arm up or limb up into that nice little package. So and we'll talk a little bit about the single actuator design in a second. It's about human scale reach. It's a lot heavier than your arm because metal isn't nearly as nice as bone these days. And then it's strong. So if you can imagine taking, I don't know if anybody's got a first grader in here, but taking your first grader and doing this. And basically this robot could do this infinitely with a first grader. It'll do a 7th grader once and then have to cool off and then do it again. But still, I mean, if you can imagine a human curling a 7th grader with one arm, and any 7th graders in the audience? Yeah. There you go. So just imagine yourself being nicely picked up by the robot. And it moves, so 2 meters a second. 2 meters a second is about 5.5 miles an hour. It doesn't sound super fast, but if you're just moving yourself around, this is actually pretty quick. And it's really quick if it's a robot and you're standing close enough to it that you're a little surprised by how fast that goes. The other aspect of that is there's very little that we want to do with this robot that needs to go faster than that. That's kind of analogous to how slow our Mars rovers go. We could make our Mars rover go faster, but we don't actually want to get anywhere faster. And so giving it all the added capability in terms of its mobility at the price of speed is just okay because it's not in the requirement list. I'm sure it would be neater to make the movie if this thing went faster, but it's just not the thing that we're really concentrating on all the time. So this is the single actuator. So just to give you a little scale on this. All right, so this is inside every joint, there's one type of drivetrain. So all 28 joints in the robot have one of these inside. That's for a few good reasons. Now, if you think again about yourself, you've got relatively robust joints here and muscles that run them, your elbow a little less so, and then out towards the wrist. So you actually get progressively smaller as you go out towards the end. RoboSimian doesn't do that. It's robust from one end to the other. First reason for that is that making a bunch of these is a lot less expensive than making a bunch of other things. So commonality of all of these parts. The second big reason is that if you're going out into the field and you need to take spares, you take a few of these instead of a bunch of other things. And the last reason is, as it turns out, if you are going out and grabbing onto things and yanking them around and doing all these other things, once you grab onto something, it doesn't really matter if it's attached to my shoulder or it's attached to my wrist. You actually need basically the same capabilities. And this is why people break their wrists. Right? People are actually really great at hurting themselves. They're also really good at healing, which is one thing we can't do. It actually works out to be a very convenient thing to have all the same joints for that reason. So some other fun little superlatives from this is that that joint, while very slow, still produces the same amount of torque as an F-150 truck. So now, it's a big difference if you've got wheels that are that big and you've got to tow a big trailer and a bunch of other things. But basically, and plus, it can generate that much torque at 50 miles an hour, details. Regardless, that's a lot of pulling power. And so if we're trying to lift ourselves, it's a heavy robot, it's about the same weight as a large man, that we can do real things in the real world. And then sort of these mechanical power numbers, think about the number of lights that you can do with that. It turns out not to be a good comparison with a car, so I left that off. All right, now, at the end of all these limbs, there's a hand. So when we did the proposal, the hand on the left is what we worked with Stanford University on. It's a very nifty looking hand. It looks really good in a proposal. Then you got to make one. So we worked with a grad student at Stanford, and I told them, OK, well, we know that we want to really interact in a forceful way with the world, and we never want to worry too much about how big a thing we can grab. Go find out how big Wilt Chamberlain's hand is and make me a hand that's the same size as Wilt Chamberlain's hand. So he did. And there's nothing in the scale from that picture. But I will tell you that it's a really bad idea to make something as big as Wilt Chamberlain's hand, because it was a really big hand. And it turned out, it was very funny, because he showed up and he's like, here it is. And it's like, that thing's gigantic. It can't grab anything. So grabbing door handles, grabbing drills, it was just too big. So I don't know how Wilt Chamberlain did any work on his house. I'm guessing it was good that he probably had somebody for that. So we backed off of Wilt Chamberlain and got down to the hand that you see in the upper right. So this is basically a human scale hand. It's got articulated fingers. We call them under-actuated, which means that there's just basically one motor that pulls on tendons, very similar to your own fingers. And those tendons then cause the finger to rotate, and if they encounter something, they wrap around it. So that's an under-actuated finger. Because instead of all the muscles that we have, it has one motor that runs all of those tendons. And you can see it does the job pretty well. But it was weak, and interestingly enough, it breaks exactly the same way that people's hands do. So I myself, you probably can't see it from there, this is called jersey finger. And so if anybody's thinking about playing football and they're of high school age, it'll be my little cautionary tale tonight. So jersey finger, it's called jersey finger because if you grab somebody's jersey and they yank it, the tendons in your fingers tend to break in something called an avulsion fracture. So it's a problem. And as it turned out, it was a problem for us too in the competition. We broke one finger per door. Fortunately, we had 3 fingers and 3 doors. And they allowed us to fix the fingers between runs. So this is not optimal. And the fact of the matter is people hurt their hands doing robust work all the time. They heal well, robots don't. And so that seemed like the wrong way to go forward. So what might be and of course the other fun aspect of all of this is that because we walk around on our hands, they actually have to be able to do that. And so you notice that the fingers actually fold back on themselves. That wasn't such it worked, but it wasn't super duper. So we went back, and you'll see the progression here of something that we call the cam hand. The cam hand is basically supposed to be able to do what you could do in a heavy work glove, which is in line with the type of jobs that we expect from this thing in a disaster scenario. So it starts from, yes, people really do sketch things on paper. And then we went and we made ourselves, and I know it's a little tough to make out because we used clear plastic to do it, but we prototyped this thing, and basically the thing you see in the middle is something that we walked around with and we grabbed stuff with, so a little puppeteering. And based on that, we felt good enough that we actually turned it into the actual hand. So without further ado, very slow. Again, doesn't need to be fast. So here's the cam hand. Now, to the best of my knowledge, again, there is no other system like this out there in the world. So what you're seeing is that basically a simple, what might be called a pinch grasp system. In that way, not much different than other hands that have been built over the years, very simple ones. But it has some particular features. So you're seeing that it can individually move one set of the fingers. The other set of fingers are actually slaved together. So 2 on one side are slaved together, and then 2 on the other are independent. I'll explain that a little more. I do believe, outside of Iron Giant the movie, this is the only self-ambulatory hand that I'm aware of. And you're seeing one of the other really important aspects about it is that all of those fingers can, just like the limbs, they can all rotate all the way around. So starting off, we need a foot. Now, not only is it a foot, but it's a foot that can be configured in a lot of different ways. It's a nice rolling foot, so we get a nice rolling contact, and a clawed foot. And on top of that, if you run the fingers in the same direction at the same time, we actually get yet another degree of freedom out of this, so a wrist and ankle. Now it's got some oomph, so here's our standard 4x4, no problem. And we've gone through the commercial hands. You can't do this with those. And you really can't do this with those. And there is no other hand in the entire world that does this at all. So anybody who climbs for fun, and I know there's some people out there that do this, this is called a cam. Cams are what are called self-locking mechanisms and are great for negative space grips. And then sometimes you just do this. Remember, these robots are here to help. So not much different, actually, than the fire department showing up with the jaws of life. Now, we'll use this hand in various ways. So here's the vehicle that we need to drive. So we're actually going to grab it right in the middle. We've got a nice joint that rotates 360 degrees plus, right? And we're going to grab the roll cage to get ourselves out of the vehicle. So very robust. But at the same time, this is actually a really hard thing to do. Push a button with most of the commercial hands. And at the same time, we have to respect the aspect ratio of a human hand and keep it so that it can actually use human tools. So in particular, the drill. Now, there are 2 tricks to using the drill, as I mentioned. One is being able to grab the thing in the first place. Actually, I guess there are 3. Grab the thing, turn the trigger on. And then the last and most important thing is you can actually hold on to it in a stable way such that you can actually do real work with it. So this is the task. We've got to cut a hole in a wall, as you might remember. So that is a drywall bit that you saw on the drill. And this is the robot holding on robustly enough to cut that hole. So here I have, just for scale, you can see this thing. It's about a little bit wider than I am. This hand actually has a capacity, every finger of it can hold up the entire weight of the robot. And there are 4 fingers, so that gives us a lot of capacity there. Again, not fast, and just like the joints of the limb, produces about the same amount of torque as that F-150 we were talking about earlier. So we haven't really experimented with it too much. The child of one of our own here at JPL, Fletcher, did, as a high school student, designed the fingers that are on here. We haven't seen any reason whatsoever to change them. If we were to change them, it actually turns out to be, it's by design, a very easy thing to do. So we can pop these things off, substitute in a different design if we so chose. Like, for instance, since these things pass by each other, they make really great clippers. And so building a wire clipping capability into these systems would be really easy. Or other things that would come along with sort of the cam aspects of it. So just to give you an idea. This is, by the way, really, really heavy. Now, I'm going to take a big turn here. Now, and I'm going to do it because I want to talk about software. But to talk about some software, I actually have to talk about this other robot first. So this other robot is a product of RoboSimian technology. Those limbs and all of the philosophies behind them can be reconstituted into a different robot, Surrogate in this case. So Surrogate was actually done for a different agency, not DARPA in this case. It's actually for something called DITRA. Now, be honest, how many people in this room know what DITRA is? Okay, we've got one person in the booth. All right, it's the Defense Threat Reduction Agency. So now, how many people in the room know what it is? Okay. So they're the people who are going to show up at your doorstep if you have an anthrax scare or a radiological problem or things of that nature. And they're here to help. And to get into that hazardous environment they need to deal with, it's not necessarily an environment that actually is in a degraded condition. It just has something nasty in it. So to move more quickly, we picked a tracked base. And then to do these probably more sophisticated manipulation tasks, we gave it arms now. So these are the same limbs that we talked about before, but really now they're just being used as arms with some caveats. And a spine. So this is another unique feature, not to be found in other robots. This is an articulated spine that can move around in more degrees of freedom, because it's the same thing. It's the same limb, those 7 degrees of freedom, so that it can do things that other robots cannot. And then finally, we actually gave it, in this case, a head that has cameras and this LiDAR on top of it. So we can actually get better view of what we're doing. So this is actually, because it's specialized toward the manipulation, using the human model of arms, specialized arms, and a head and neck made more sense. Now, one of the neat things about it is because these are really robust arms, and we have this long articulated spine, we can do nifty things like lean over and brace ourselves with one limb while reaching with the other one. And so this is another sort of first-of-kind demonstration. Now, so giving you that robot, because I'm going to show you some of the demonstrations of software based on that, because they're very similar to the ones we use in RoboSimian. So we want to break things up. The robot needs to do the human hard things. Humans are really bad about directing robots at the joint level to do anything. They're also obviously not as good about trying to pull in on the information. So pictures, they're going to come back in 2D, and the humans really have no way of combining those things up and sending that information back to the robot in any useful manner. So what we want the robot to do is build its 3D map of the world itself. So it's going to do all the nifty math after it takes in the pictures and the laser rangefinder that's on it. It's going to execute these behaviors, and we'll talk about those a little bit more. And then at the very end of it, a human to control, to joystick the robot in a way that it doesn't, when it touches things, doesn't mess up is hard. However, the robot can sense it, and if it senses it, it can actually stop itself. So it's got that last little bit of control as well. The things that the human does that robots are rotten at the moment, object recognition. So the classic example is ask a person from anywhere in the world what a chair is and show them things. The probability is the person's going to have a high rate of success at doing that. That's a very difficult thing to get across to a robot, because all of the rules that you would want to have, it's like, well, a chair is a thing with legs. Well, sometimes. Sometimes it's got 4 legs, sometimes it has 3 legs, sometimes it has a lot of legs, sometimes it doesn't have any because it's sort of on a little pedestal, and the robot's like, time out. But a human, that's a chair. In our case, we care about valves, for instance, or doors. And the robot trying to figure out a valve, of all the valves, we could download the catalog of all known valves, the master catalog, straight into its brain, and it might get some of that, but what if that valve was now bent in some other way? Well, we'd have to come up with algorithms, which we can, that would allow the robot to recognize it, but it's hard. What we've got on this planet are billions of people who know what a valve is, so just let the people do it. Someday robots will be smart enough to figure that stuff out for themselves, but we're not interested in someday, we're interested in soon. And soon means people are the ones figuring that stuff out And then the user can give the robot cheats. So in the case of the valve, which we'll talk about a little bit, the operator actually just sticks the valve on top of the world map for the robot to use in its planning. So other key things, right? These are the things that the robot needs to be able to do. These are some illustrations at the same time of what the RoboSimian body plan does. So we got to plan all of this stuff. And there is some fantastic math, and I'll point to the front row. That's some of the people that are doing the fancy math. That's my term. You can ask him later what he actually calls it. So it takes fancy math to actually plan all of this stuff. And it can't just be plan one limb and what it does and those 7 degrees of freedom. It's got to be plan what the entire body does at any one time. The other bit is you got to move around in the real world. So in this lower left, this is collision checking. So I'd like to reach over there. Well, there's a bunch of stuff there. How do I reach in there? And actually trying to figure out what you want to do doesn't collide into something else is a difficult problem in itself. So there's software that takes care of that. And then finally, sort of in the lower right, is a bit of the whole body aspect of that. So now moving around in that 3D environment in a way and planning how to do that properly. So a little bit more detail on that. So on the top is RoboSimian showing that kind of body motion. So RoboSimian just sitting on its feet, we'll call them for a second, sitting on its feet and trying to reach with just one limb without moving the rest of its body doesn't have a lot of reach. RoboSimian, rolling its whole body, planning what to do with all of those limbs at any one time, actually has pretty considerable reach. And it's got to plan all of that while keeping itself stable. So an added little extra fun. And then the same sort of thing, but for surrogate down at the bottom. And in this case, it's using its spine and its limb at the same time to carry something out. So rolling all of that stuff together, here's a surrogate doing a valve turn. We really love turning valves. Valves is great. So it looks out into the world with its eyes, its cameras, builds a 3D environment. It actually, we have some other fancy math that actually lets it figure out where to park itself so that it can do its job later. It's going to come up. It's going to say, hey, operator, I've got this thing in front of me. What do I do with it? And the operator is going to say, here's what you're interested in, and I want you to, and you notice there's basically noun verb. You know, this is the behavior. I want you to do this thing to this thing, and I'll tell you what it is. And then the robot takes over again, and it says, okay, well, I got to grab this valve, and I got to turn it. And it plans for itself how to actually execute that motion. Now you see it's using some commercially available grippers here that aren't. These are the ones that we found not to be quite strong enough to do most of what we would like. And if you're watching, it's moving both its limbs and its spine at the same time. And it's not as obvious in this case, but the other limb in certain moves is also there to keep stability. So if it's reaching, you'll actually see it move. If it's reaching out with this one, it'll actually move the other one out. So you get a little surfing action from your robot. So, as all that coming around back to the trials. So this is what it looks like. This is, we showed you a little bit of this before. It's a human scale, so it's relatively easy to pick up. It's robust, so we're not really worried about it. So we just grab it, take it where it needs to go, and does what it needs to do. So this just happens to be a little bit more of the video of clearing out the debris. One of the other reasons to look at this particular video is because we have this generalized system, it actually allows the operators to figure out new ways to use it that we didn't expect. In this case, it was, how do we get all of these pieces of debris out of the way? The DARPA, when they set this up, really thought what was going to happen is that people would come in and they would grab every individual piece of debris and dump it over the side. We decided that was inefficient. So we roll up to it, take a look at it. You don't see the sweat coming off of the two guys but there is a little stress. So they're grabbing these things, Wait for it. 0 points. Not doing well. A little stressed. By the way, you'll notice that the robot doesn't move very much, and the operators talk a lot. This is why we want to be a patient robot, because robots will always be waiting for humans to come up with a really creative solution. Oh, let's just grab this thing, and we will drag it out. So we actually cleared, and I forget, we got 1 point for every 5 pieces of wood or something like that. So we were able to go in there and then clear it all out. So we actually ended up getting full points for that particular thing. So lessons learned. This is an interesting thing is that in the top, by the way, we finished 5th out of 16 teams. We were quite proud of that. But of the 5 top teams, we call ourselves the cool kids. Out of the cool kids, there were humanoids, and there were robots like RoboSimian, and actually another one called Chimp from Carnegie Mellon University. And Chimp, as you might expect, kind of looks a little bit like RoboSimian, but bigger and meaner. That having a flexible system is a really good thing, and that we can let the operators explore how it does everything. However, one of the things that's still hard is translating these human goals into robot goals and trying how to do that effectively. And then, frankly, trying to figure out how to balance the dexterity of your robot and the robustness of the robot. It's easy to build a robust robot. It's easy to build a dexterous robot. It's really hard to build anything that combines those two things. So, and we're still trying to find the sweet spot of that relative to the job that the robot needs to do. For completeness sake, I was going to point out that we actually have other limbed robots here at JPL. They're really big ones, like Athlete, which is basically the coolest truck in the solar system. It will load and unload itself for you. And then in the middle, we've got cave climbing robots. The lemur systems hopefully will be deployed into the caves of New Mexico sometime later this year. And systems that are very similar to that. It turns out that climbing around on the outside of spacecraft for inspection purposes is basically the same type of robotics problem as climbing around inside of caves. You just swap your microspine grippers, which are for the caves, for artificial gecko adhesive to climb around on the outside of spacecraft. So this is sort of, and this is not a complete list, but it is basically the core of folks who have, in some way or another, made RoboSimian possible. JPL, long list of folks, UCSB, Caltech, and Stanford, and the Art Institute have all contributed in some way or another to what you saw here today. And then it's always nice to thank the people with the checkbooks. And I'd say with that, we can open up to questions. So there's a microphone out there. I do believe the idea is that if you'd like to ask a question, you should find your way to a microphone.
Hello.
Yeah.
A couple quick questions. I know you guys like your acronyms. I'm wondering what ATHLETE stands for.
John, what does ATHLETE stand for?
All-terrain, hex-limbed, extraterrestrial explorer.
All right. I knew somebody would know. And I'm sorry if you answered this earlier. Were there weight restrictions put on this thing, or how much does it weigh?
So it weighs about 125 kilos. There are no weight restrictions, but there are practical limits to how big your robot can be because it has to fit into these human type of environments. So I believe Chimp is closer to, so I'll switch units on you and I apologize. So I think it's like closer to 400 pounds. So the Atlas systems are 300 poundish. We're kind of in the middle, and I think the smallest robots are 100 poundish. The Hubos are roughly in that category.
Okay, and then my final question was just kind of a general question about the power source and limitations you've had or struggles you've had with that and how it affects the design and the strength of it.
Because it's all electric and on purpose. This is a very well-known technology. this electric stuff. And we actually borrowed the design of the battery that runs this from electric motorcycles. This has been, the fact that we now have hybrids and electric cars has been great for the stuff we do, because now, and actually laptops, which is where, so all the vehicle batteries are actually coming from laptop technology. So we now have these very compact power sources that we can use, and that's been great. It's still pretty challenging to put, so for all the well, for all the people who like, did somebody say geeks? You know, so for all the nerds in the audience, we actually have a 2 kilowatt hour battery in there, so that should be able, and getting that much energy in such a small space is a relatively new thing, but you know, that's been a huge benefit to get the technology from other industries.
Thank you.
Okay.
My question has several parts. Your actuator you showed, does it have any gears in it?
Yes.
Yeah.
So this, let me pull it back out. I didn't really go through the elements of it.
So my question is, does it have limitations on how fast it can accelerate? And the reason I'm interested in that is eventually you want to have bipedal motion. And am I correct in saying if you're trying to walk like a human walks, you have a certain pendulum, and you have certain, you have to have certain rates of speed and acceleration to avoid falling over. Mm-hmm. Mm-hmm. Okay.
So we differentiate, you know, this is sort of the tortoise and the hare, and the tortoise uses what we refer to as quasi-static motion, which is basically what we are, right? So you could freeze this robot at any point in time and it wouldn't fall over. That's different than actually most everything else that moves around, which is dynamic motion in some way or another. So whether you're quadrupedal or bipedal, most animals get around in a dynamic mode, sort of the pendulum action that you're talking about. And yes, you do need to move fast enough to make that happen, or in this case, you have to actually be able to produce enough power to move a certain mass that fast. And so that actually is a significant issue for us, because normal off-the-shelf technologies don't give us enough power density to pull that off. Mm-hmm. For instance, one way around that is a lot of the bipedal systems have hydraulics instead. And so the power density of the hydraulic system is better, but hydraulics as a system are maybe not as much.
You don't want to do that. Yeah.
Right.
All right, so that's coming. Thanks.
Yeah.
So the robot, I noticed that the valves that were shown on the presentation you were facing it horizontally. Mm-hmm. Does it have limitations on valves or something like that that would be on the ground or on the ceiling?
As long as it can reach it, probably not. And so we talk about what the robot can do, and just like yourself, like you can actually get yourself bound up in a position where you can't get to what you're trying to do. So if I got my arm stuck kind of up in here, you really can't do much either. So as long as the robot can put that valve in a space relative to itself, that it can make this motion, then it shouldn't have a problem whether it's down on the ground or on the ceiling. Obviously, if you can't reach it, that's a problem too. In RoboSimian's case, that's an interesting problem if it's up above, because while we can go bipedal, it's only if we have something to work with. So we have to climb up the side of a wall to reach something higher, which we can do. And it works for most ways that these types of facilities are built. But we couldn't just rear up and grab something that was up above us. That would be the basic limitation. But otherwise, you know, it's just another 3D problem to the robot.
Then does it have the capability to kind of like drag things into pile, climb up, and then do that?
Sure. So it physically would have that capability. It doesn't have a software behavior for that explicitly at the moment. And probably if you want to do something that complex, that's where you're again you're gonna trust that you've got a human on the other end that's going to come up with a creative solution like that. So looking around in the room, trying to determine what you could grab in the room that's robust enough to pile into a way of getting yourself higher.
And my final question is, you know how you said that when the camera gets a image and sends it to the computer, you can't figure out sort of the 3D stuff? Mm-hmm. if you just have a like the way that the robot's designed, like if you had a camera on like the shoulders, can't you do like a bunch of trigonometry stuff and figure out how far stuff is?
Actually, that's exactly what the robot's doing. So you just described machine vision. So now you don't need an advanced degree to do that because you just figured it out for yourself, which is great. So yeah, you don't. But the person, like you don't. If it's just pictures that are shown to the person, the operator can't do that math that's going to then turn into an instruction back to the robot. So that's why we want the robot building the map.
Then can't you send that into like an Oculus Rift or something and then have it like that?
Yes, absolutely. But the interesting thing is, if you send it to the Oculus Rift, you've already created the map. So while the Oculus Rift or something like it might be a useful way for a human operator to interact with the robot's not going to base its actions on the information that's in the Oculus Rift. It's going to base its actions on the information that it carries around in its own system, in its own head.
Yeah, thank you.
Sure.
Hi. So with the software engineering behind this, was most of these algorithms, were they written in Python or C, do you know? And
C.
Is C, and is any of this available online for
No.
people who are doing none of it? Will it be eventually?
Yeah.
Or?
So, it's the best way to answer this question. There are certain
Government paid for it.
there are certain legal hurdles to us sharing code.
Okay.
Is the short answer, or the shortest answer I think I've got to that question. Yeah. So hopefully, but where you would see this stuff is in published papers and things like that. So as long as you don't mind writing your own code, the way we did it, the actual methodology and the algorithm that informed the software is something that would be published and available that way.
You mentioned early on that this is not just an academic project. You want to be able to actually deploy this.
Mm-hmm.
Is there a path organizationally going forwards? The DARPA competition is to stimulate this kind of technological research to sort of team up with the other winning teams and cross-pollinate to make a finished product, or for DARPA to take the best of all of the team's work and move forward with something else, or are you planning to go it alone moving forwards?
There's no specific mechanism in place to deal with it the way you described. But however, every team is allowed to do whatever they want because it's their intellectual property. So for instance, RoboSimian, both the physical design and the software, is under license to a local company here called Motive Space Systems. And so they are looking for commercial applications for the system and building them under license to JPL.
So there's no reason they couldn't go to other teams after competition and say, we want to pull this in.
Yeah, no, they absolutely could. Yeah, and that's probably how a lot of this would actually happen. Now, as an interesting aspect to that, after the trial, actually right before the trials, the winning team from Japan, Shaft, was bought by Google. And Boston Dynamics, which provided half of the field with the Atlas systems under contract to DARPA, was also bought by Google. So basically, Google bought half of the competition's technology.
Right.
And that's the other way it happens.
Right. Thank you.
Sure.
Hi, I was curious of what type of control architecture there is for RoboSimian as far as the motor controls go. So is it centralized control, decentralized at the axis level?
Yeah, so every, actually, I have a prop. Hey, I've got a prop. So sitting on top of this is a set of electronics. This little magic silver box, it's not a little black box, it's actually a little silver box in this case, is a commercial motor controller. And it all speaks EtherCAT. And so this is a highly distributed architecture for RoboSimian specifically. And it allows us to do some things like these modular actuators, so we drop them in that way.
Were those developed in-house or purchased?
No, so these actually happen to be Elmo, if you're interested in the brand name, yes. So Elmo controllers. They're not, we are applying technology that was not really designed for this purpose for our needs. So there's probably, in the future, there'll be better solutions than this.
Are those running in position mode then, at the axis level?
Basically. Now, Elmos have a host of different modes that they can actually use. So you can kind of tweak your control to meet your need. So whether or not you're doing just trajectory following, or if you're in a force control mode or something like that, you can move to different modes.
Okay, thank you.
Sure.
So obviously the hands have a lot of power in order to lift things like cinder blocks and other large materials, but I noticed that they're also doing very delicate things like pressing buttons or manipulating objects that are meant to be manipulated by humans who obviously have a lot less strength. So how is that controlled so that, obviously we saw that it could cut through things like plywood so that it doesn't break things that are more delicate? Is that done on the robot level? Does that evaluate it, or does the human operator control how much power it puts into its motion?
So something like a button push is, it's actually not the hand. There's a sensor that senses force that's behind the hand, sort of at the wrist. And so if you wanted to tell whether or not you're pushing the button, you'd be looking at that particular sensor to tell how hard you're pushing. Some of the bits about grabbing stuff, at this point, the hand doesn't really have the ability to, a sense of touch, or even how hard it's grabbing things. So if it's not robust, like if we try to pick up an egg with this, it would just crush it. So we try to pick up on things that are relatively robust in themselves. Like the drill is a very, it's designed for taking a lot of abuse, and we abuse it. So.
Thank you.
Yeah.
How simple are the controls for the robot to use?
Simple.
I'd say powered,
Well,
I guess.
Actually, so I would answer, they're really simple, but relative to what they do. And you saw the user interface that we had. So it showed for instance, the valves, the picture of the valves, and the user flew in a valve on top of that and then said, execute this behavior. That's the simplest version. And that, as long as it's within those sets of behaviors, you can actually get that down, and we have to running on a little robust tablet that you could, basically, for very simple tasks, that's all you really need. For the stuff that we do, you can go all the way down into the lowest levels of the system and actually get every joint to do what you want it to. But that's a very time inefficient way of getting things done.
And how long and what is the range of distance that you can communicate with the robot, and how long does the robot run with the power source?
So it runs on normal Wi-Fi. So I think we probably have a couple hundred yards at most. At the way it's set up right now. You'd actually have to, to make this a truly fieldable system, depending on where you're going to apply it. Like if you wanted it to go into a Fukushima-like scenario, you're probably going to use different comm gear. The comm gear that we have is that dictated by DARPA for the trials, or for the finals. So it's sort of limited to that normal Wi-Fi kind of system.
So then how would you communicate it when you said, like, for example, the caves in New Mexico? Like, wouldn't that block the Wi-Fi?
That is a very good question. So we use those caves as a stand-in for the caves that we believe to be on Mars. And if we get down to that, then we're going to use some very sophisticated comm technology, including things like optical comm with repeater stations, for instance.
And how long can you run the robot?
So RoboSimian, as I said, it's got this 2 kilowatt-hour battery. We don't actually know how long we can run it depending on what you're doing. We don't use, so I'll answer this question this way. We're only allowed an hour to do all of the finals, and we're pretty sure that we can't run at 2 kilowatts. So we know that we can run at least an hour. In practical application, that 2 kilowatt hours, if you're careful about what you're doing, and the robot spends a lot of time sitting around, which is a very likely event, then its actual time of operation could be 8 to 10 hours. So, but that's mostly predicated on the fact that it's sitting around a lot. I think oh yeah, there we go. We got some questions phoned in. All right. So these are sent in. So Coolbot7 asks, what tasks do RoboSimian tackle autonomously versus those that are human-controlled? So RoboSimian actually uses a system that's very similar to the way we deal with the rovers on Mars. And we call it supervised autonomy. And as I've been talking about behaviors, basically every behavior is autonomous in itself. So it takes input from the operator, and then it executes that particular behavior autonomously, including things like noticing air conditions and stopping itself and calling home. So within a particular behavior, it's autonomous. The way that those behaviors get linked together are the supervised aspect of it. So those are all built up by the human operators. So hopefully that answered that one. Daniel asks, how durable is RoboSimian? What temperatures can it withstand? Water, flooding? So it's pretty durable. Little known fact, we've actually rolled it once. It was fine. It's all good. We know it's at least that durable. And it really is. You can see the battle scars on it. I've challenged everyone to see if they could break it. And we haven't yet, although we've bent it just a touch. So it's physically very robust and designed that way on purpose. One of the nice things about not having a head and neck is that you don't have a head and neck to break off. So that's one of the advantages of that. The temperatures it's going to withstand. So these are normal commercial electronics. So we're talking about, somewhere below freezing to somewhere warmer than comfortable temperatures for humans. So 120 C or so. And actually the robot, in doing its job, there's a lot of waste heat, so it actually heats itself up pretty toasty. Water and flooding. So this version is not water sealed at all. We are working on elements that of a system we're calling RoboSimian. And for those that are quick on the draw, you'll notice that that's just a really fancy way of saying sea monkey. So RoboSimian is in fact designed to be fully immersible, and in fact the design is probably good to about 50 meters or so. So we're hoping to bring that design along as fast as we can. A fieldable system, even terrestrial, would have to be certainly weather sealed. So call it a good camera level of sealing to keep the dust and water out. Aldo Navarro asks, this is the last one, is RoboSimian able to work in space like outside the ISS to repair or perform work? Not as it is. So again, these are commercial electronics. When we actually build systems for space, it's a whole different set of bits and pieces that go into it. That's what turns these research robots into flight robots, is going through and working out all of the issues with vacuum and cold and hot, and replacing the components as necessary to do that. So as is, there's very little of, at the individual piece part level of a RoboSimian that could be translated directly to a flight application. Now, the concept of the robot is very much something that we would like to see in space. The iris concept that I was showing you that would be out for inspection is effectively very similar to RoboSimian. The robot that we use for testing here on Earth, called Lemur, for the iris project, is basically a small RoboSimian. It's actually, body's about yay big and limbs are about yay long. But otherwise, from a squinty point of view, a very similar system. So we very much hope to be able to put that kind of thing on the outside of long-duration spacecraft, in particular for inspection and maintenance at some point or another. So that's the last question I have. Does anybody else have any more questions they'd like to ask? And yeah, yeah.
Would it be able to hear or send audio to the operator?
Good question. That would be spiffy, and that was an intention. One of our intentions when we first laid out the design. It's not something we've done to date, but absolutely you would want to be able to put ears in the system. If not for the robot to use as information, but it would be a really great cue for humans. You know, humans take in information in all sorts of different ways, and the more channels of information that we can provide the operator, the better their understanding of the situation that the robot's in is going to be. So having some sort of audio pickup would be fantastic, because it could be just as simple as, I'm looking for a leak, I need to listen for it. It's one of the very basic things a human would do. So not putting some sort of system like that on an actual fielded robot like RoboSimian would be probably silly. So. Cool. Well, if there's nothing else, thank you very much for all of your attention. By the way, if you want to talk to guys that are working on it,